Okay, so what we're going to do now is move on to talking about function spaces. There's some additional separation conditions I mentioned earlier, regular and normal, which so they're in the notes, and there's a few exercises about that. There's also an exercise there which walks you through the fact that spaces in algebraic geometry are, in some sense, never Hausdorff, and in some other sense, always Hausdorff. Yeah, well, it's life. Well, the point is that there's something more fundamental than any of these ideas, which you can manifest in various different ways, right? So, the idea of being Hausdorff is deeper than this definition for topological spaces. So in some other setting, you can find another definition, which is the more appropriate one. And in that sense, spaces in algebraic geometry are also Hausdorff. Okay, so if you remember, I started these classes by sort of slightly, describing three ways, roughly speaking, of thinking about spaces, right? And that was, well, space is a stage for things. Space as a stage for motion, and then space as a, well, let's say, a channel for communication. Well, we've spent the first half of the semester sort of talking about space as a stage for things, right? All our examples of spaces are things you could sort of imagine as static things just sitting there, right? So spheres, tori, CW complexes. That's where we've been sort of working conceptually. The next half of the semester is here. So from now on, we're focusing on function spaces, and, well, at least implicitly, the idea of a function space is that it's telling you about motions, right? That's exactly how they appear in physics, and it's not a bad intuition for the mathematics either. Okay, so we want to talk about space as a stage for motion and introduce the idea of function spaces. So let me do that with some simple examples before we get into the theory. Maybe you think 3 is a bit strange, but one of the most popular sort of sub-disciplines of mathematical physics these days is the ADS-CFT correspondence, within which this is basically the whole point. So there's a lot of work being done around this idea, speculative still, but nonetheless kind of interesting. All right, so you've all seen this since your first calculus class, but now you actually know some topology, so you can do it properly. All right, so what's a motion in a space X? Well, as you all know, something, say a particle, moving around in a space X is just a continuous map from R to X, thinking of R as time, right? Now what you're used to thinking about, well, it depends whether you've done physics to some degree or not, but if you're just thinking about ordinary calculus and motion of particles and so on, you mostly would have been thinking about X as physical space, like R3. Now, if you've done some physics, you've learned to think about spaces such as configuration spaces, say, of extended bodies, right? And then the body evolving in time, say, just moving or parts of it reconfiguring themselves is also a motion in space, but in a configuration space. So let me give a very simple example. course, we've learned to be a little skeptical of that idea, but all right. So it's either physical space or configuration space. All right, so what do I mean by configuration space? Well, suppose you're studying a system which consists of two rigid rods, well, this point being fixed, and at the end of that rod is attached a second rod. This point can move and that point can move, but well, they're rigid, so those lengths don't change. Well, then the configuration of that system at any given time can be described, well, its position anyway. I mean, the sort of position part of the configuration of that system at a given time is described by two angles. Okay, so the evolution of that system over time is described by a continuous map from R to the torus, right? Two angles, and they're independent of one another. You know, don't talk to me about this rod hitting that one, okay? Of course you can worry about that, but so this is ft is theta t psi t. Yeah? Okay. Well, so suppose we're in, I mean, either one of those situations. So X is just physical space or a configuration space. What would it mean to say that the motion is periodic? Well, it would mean there is some real number t such that, so let's fix the f. So f is the motion of our system, and it's periodic if there's a t such that f of little t plus kt is equal to f of t for all t in R. Right, that's what it means to have period t. Sorry? Yeah, thanks. Yeah, otherwise that's not so sensible. Okay. But we know sort of a way to think about such continuous functions. I mean, this condition in a slightly more sophisticated way now, right? So the subset, say zt, which is all those multiples, so that sits inside R. It's a subgroup. It's closed under addition. And I can look at the equivalence relation on R, which says two real numbers are equivalent if their difference lies in that subgroup. That's the usual equivalence relation you'd put on something to form the quotient of a group. We discussed that in the last tutorial. So the quotient of R by that equivalence relation will denote R mod zt. And well, we know that that's a topological space with the quotient topology, and we know that's just homeomorphic to S1. Okay, so if f is periodic, so a continuous map from R to X is periodic with period t. Well, that's if and only if it has the correct property with respect to this equivalence relation. That is, if two times differ by an element in zt, then f sends them to the same thing, which is to say that that function factors through the quotient. That's exactly the same statement. So it's periodic with period t, if and only if it factors as a continuous map out of the circle. Say f tilde. As in the diagram, which says, well, here's R. There's the original f. I can go to R mod ZT, that's just S1. And that's what I mean by factoring, right? So if F is a continuous map, which is periodic of period t, then there exists a continuous map F tilde making that diagram commute, and vice versa. Okay, so periodic motions are exactly the same thing as continuous maps out of the circle. That's what this says. And that's the whole point of the circle, in some sense. All right. Okay, so we've talked about motions. Motions are continuous functions, but I haven't talked about function spaces yet. So what I want to do is now motivate the idea of collecting motions together to form a space. And to do that, I need to talk about continuous degrees of freedom sort of among the functions, right? And the easiest way to do that is to talk about the motion of an extended body like a string. And to do that, before we consider a string moving, which is made up of an infinite number of particles all moving, let's just consider two particles moving. Right? So given two motions, so i.e. continuous functions, let's say F1 and F2, the whole point of the function space is that it allows us to talk about that pair as a single continuous map into the product. Right, I mean that's just the sort of defining property of the Cartesian product of topological spaces. It's a continuous map. Well, so you could think of that as, say, if x and y were both Euclidean space, you could think of that as a pair of particles moving around. So what about an infinite number of simultaneous motions, say particles? So that would be something like Fi from R to Xi. Well, as we know, those determine a continuous map from R into the Cartesian product of all the Xi's. Now, the next step is to consider the situation in which I itself has a topology. Okay, we've never discussed that before. So if we're just considering sort of particles moving around independently of one another, we can combine all their motions into a single motion. Well, I mean, a collection of particles distributed in a continuous way, that's one definition of what an object is, right? So to talk about the case where I has a topology is basically the same thing as to talk about a continuous object undergoing motion. Well, let's say, for instance, a string. Well, here's a picture. So let's suppose the string is attached above the interval 0, 1. The endpoints are allowed to move. Well, then for each I between 0 and 1, the particle, so to speak, which belongs to this object above I, is undergoing its own motion just along a single coordinate axis. And so let's call that Fi. Right? Right, so Fit is the height of the string above position I at time t. Well, so there's an index set I, and there's a family of particles indexed by I, all moving. So I could accumulate all those motions into a function of this form from R to the Cartesian product. But that's clearly not a very sensible notion of a motion of the string, right? Because if I and I prime are close, you would expect Fit and Fi prime t to be close. Otherwise, it's not a string moving, it's just a bunch of independent particles. Okay. All right, so we expect, so that is to say this is not the Cartesian product and functions into it is not the correct set of functions to describe the motion of a continuous object. If there's a topology on T, somehow that topology needs to be manifest in the definition. So we'd expect, as I just said, that Fi plus delta of T should be close to Fi of T for delta small. Right, so there's basically two ways we could try and arrive at the correct definition of a motion of the string as a continuous function. So the first one you will have seen, I expect, which is we just ask, so suppose we've got all these Fi's, the motion of the points, what constraint can we put on that collection of functions to say that it represents a continuous motion of a string, that is a connected object? Well, we could ask that the following map itself is continuous. Right? So given the Fi's, I can write down this function, and I could ask that that is continuous. That's saying something like this, but in fact, a little more even, right? Okay, so this would be one way of having a precise definition of what it means. So a continuous map like that would be a candidate definition for a continuous motion of the string, right?
Sufficient, or do we need uniformly continuous or something else?
Yeah, so there's uniform continuity around, that's right. Yeah, so we'll... I mean, the precise connection between the family of functions Fi and continuity of this, I prefer to discuss it through the following idea, which is, I mean, of course, connected to the fact that this is compact, and so in fact any continuous function defined on this is uniformly continuous, and this is indeed what allows us to, in the end, put a topology on this space of functions. But we'll come back to uniform continuity. So another reasonable way to talk about the motion of a string would be to first say that, well, the configuration of a string is itself a continuous map. Let's say H. Right? And what I've drawn there is the graph of a continuous function. Well, so that means that the set of continuous functions from 0, 1 to r is, as a set, sort of the set of possible configurations of our string, right? And if a motion of, say, a particle or of, this system of coupled rods is described by a continuous map into the space of configurations, well, then it would be plausible to define the motion of a string to be a continuous map from R to the set of configurations of the string, which is the set of continuous maps from 0, 1 to R. Okay, so the problem we have to set for ourselves is to make this into a space, right? So this is, well, in fact, a metric space, and therefore a topological space. And the set of continuous maps from R to that topological space is, in fact, in bijection with the set of continuous maps from this pair to R. So these 2 points of view are the same. Okay, so these two notions of the motion of the string agree. And this is the sort of prototypical reason why we put topologies on spaces of functions, and why spaces of functions are crucial not only to functional analysis, but to physics. Okay, so we'll get into that next lecture.